Okay, Assalamualaikum and very good morning. Um, this video was recorded to give up the remaining topic that I did not manage to cover during our last online class. Okay, just some review on what we have been learned in uh, image restoration. Okay, again, in image restoration, there's a three part. Okay, it's divided into three part. The first one, we assume that there's no blurring function. The only um, the only uh, the only degradation effect that or the degradation factor that affected your image is additional noise or noise. And then what we do, we try to model that noise, because normally noise is a random signal, so that's why there's no deterministic function to represent the noise. So since it's a random signal, then any random signal or random number, if you previously learned about it, it can be represented in terms of PDF, which is a probability distribution function. So that's why we try to develop, or we capture first. If you talk about the condition where your image is only affected with additional noise, or integrated with additional noise, what you can do is that, for example, let's say that is the system is your camera, so you just capture a plane surface, or if you cannot access the camera, then you can have a sample of image which is captured by using that camera. You just find the background which is represent the plane surface. Then what you do, you plot histogram. Once you have the histogram, you can normalize your histogram. Once you normalize your histogram, then that is actually a probability distribution function, and then you need to know or identify the shape. Okay, based on the shape, then you can conclude on what type of noise affected your image. Is it Gaussian? Is it um, exponential? Is it uniform, and so on? Then from that, you in the restoration process, that is where you try to find out what is actually the suitable filter that can tackle that type of noise, so you can apply at the restoration process there. Okay, however, for the second case, which is your image is only affected with blurring function, then of course you need to model the blurring function. Okay, and then in order to model the blurring function, then there's a three approach. One is through observation, the second is through experimentation, and the third one is through mathematical models. So this is how the purpose the purpose of these three approach is similar, which is we want to know the equation that represent our H over here. Okay, we want to find out the H that represent our blurring function. Once you know our H, then it's easy for you to find out the way in try to reverse this process. And doesn't matter which approach you use. Actually, once you find your H, then in order for you to find or to reverse back that process, so you can get the F head, which is the predicted output is after you restore, doing the restoring process. Okay, in or in other words, in restoring process, what you need to do is, instead of applying a lot of or several of filter as the first part, the only way to tackle the image which is affected to, with the blurring function at the restoration block, then you need to apply what we call as an inverse filtering. So this is the inverse filtering, because at this case, or at this moment, you already, of course, you know your G, and then you already estimate your H based on that three approach that I have been discussed before. Then you just can divide between G and your H, then you can get your F head. Of course, this is done through the frequency domain or in Fourier transform image. So once you get your F head here, then you need to inverse Fourier transform to find a small F head, which is image in a spatial domain to get back your image. And inverse filtering is very powerful. It's not just tackling the second case, which is your image G only affected with the blurring effect or blurring function, but if inverse filtering also can manage to solve the third part, which is let's say your image G is affected not only with the blurring function, it also affected with additive noise. Okay, so if both case or if both factor affected your or degraded your image, then you can also use the inverse filtering. However, it's a little bit tricky to apply the inverse filtering at this case, because you still can divide between your G and your H. So okay, so what will happen is that once you divide between your G, when your G is divided with your H, okay, from, let's say this is your G again, and then if you divide with your F with your H, then it's become like this. And now the problem is, again, our objective is we want to make sure that of course we want our F, our objective is we want to make sure that our F head as close as our F. So that's mean from this equation, okay, once you divide G with H, then you can simplify as this equation. So you can find out that to make sure this one is close to this one, this component should be very small or close to 0, because if this one is dominant for this expression, then your mission to make sure that your F head is close to your F is failed. So that's why now we want to make sure this part should be close to 0. So you can again, this thing is explained it here. If H has 0 is if H has 0 or small value, the last term will easily dominate the estimated F. So means that you need to make sure from here, you need to make sure that this one should not 0, because if this one is 0 or is close to a small value, then something divide with a small value or 0, this one will become almost infinity. That's mean this thing is dominate this expression. So that's why in order to avoid that, you must make sure that your H value is very large or is not close to 0 or very small value. So we play around with that equation or this expression. So how we do that? Actually, how we want to make sure that or avoid this component, this H become 0 or have a small value. Okay, again, what we do is that actually we will cascade. Okay, let us just go to this slide. Okay, again, this is the same expression that's as before, which is this one. Okay, this one. So you can see that this is the same equation. So of course, this is the third cases where the image G is affected with two degradation factor, which is blurring function and additive noise. So to find our F head here, then you need to divide between your G and your H. This is inverse filtering. So let's say I write or I try to declare another variables here, which is H head. So the definition of h head is equal to 1 over h. Okay, h head is equal 1 over h. So if I replace my h with h head here, so it will become multiplication like this. So you can imagine, let's say this is your blurring function, or your blurring functions, and then of course your blurring function should be a low pass filter, because the blurring function, the characteristic is always blur the image. So something make the image more blur is actually a low pass filter. So if you plot the h head, which is equal to 1 over h, it should look like this. Because 1 over h, it should be something like this, where because at this point is very small at this corner, so 1 over very small become very high here. The one that is very maximum at h, 1 over h, because h the maximum will become the minimum value at the center. So this is 1 over h. So from here you can see that if you want, okay, again, if you write the expression longer by replacing your h with your h head like this, so you will find out, in order for to make sure that this one become dominant, you must make sure this one become very small or less than it's close to 0. So if you want to make sure this one close to 0, this one is cannot be controlled, because it's a additive noise, it's a random number, of course it cannot be controlled. This one you can control. Okay, this is because you can see over here, if you want to make sure this thing become very small, then this one should be very small. So if you see in this diagram, the one which containing a value which is very small is at the center, and the one which is very big number that represent h here is at this corner. So now we want to make sure that this corner is removed from this process, so that this expression become very small. So how to do that? Because of course this is this thing is very represent the whole h head. So how do you want to remove this corner? So one way is that you are one way to do that is by cascade this equation with another low pass filter, because you can see that the one which have in this h head, the one which is have a very high value is at the corner. Remember that at the corner we always represent by the high frequency. So let's say if I multiply this h head with another low pass filter, which is I try to set the radius which is around this center. So then what happened to this corner, what happened to the value at this corner? Of course it will be distorted. Okay, it will be distorted by that multiplication process. So that is what we do. As you can see, one way to remove this corner is by you are multiplying your h head with another low pass filter with radius r, whereby later you can set this r. So it is actually the ideal low pass filter, because this is the equation of that things. Because anything, if the value here is low than the radius r, then h new here become your h head. Okay, if the value is more than r, then it will be distorted as 0. So this is actually the ideal this is actually an ideal low pass filter, because anything pass through, it will multiply with 1. Anything with more than r, it will multiply with 0. So from this expression we can convert it into this way, where anything less than r, then you just pass the value h head. Anything which is more than r, then you distorted with that signal with 0. So from here, then you can set the radius or the ring there, the circle there, must around this surface, this at the bottom. So now if you set some radius which is at the bottom here, then you manage to distort, or you manage to destroy this value at the corner there. Okay, this is example the effect of using or cascading this process with another low pass filter. You can find out this one is your the ideal image without any blurring effect, and this one is your image G. Okay, of course this one you cannot be obtained. The one that you obtain by using your camera is this one. Okay, let's say you already find out that this is the H that, okay, of course at this, I think this one they using the third way, which is through the mathematical model in producing your H. Once they know the H, they divide your G with your H, and after you divide your G with your H, this is what you get. So you can see that what happened actually, this one is without cascading with this ideal low pass filter, or without multiplying the low pass filter. You are directly divide your G with your H, and then when you display the image, you see nothing's there. So this happened because, why is this happen? Because of this component is still dominate. Okay, this component is still dominate. Okay, this component is still dominate. So that's why when this component is dominate this expression, then you cannot see image there. Okay, the image has been destroyed by that dominated component, which is the additive noise. So once you cascade with that ideal low pass filter, you can see that that is the effect. Okay, this is the image after you cascading with the low pass filter with the radius 40, and this one is 70, and this one is 100. Okay, from here, which one is the best? I believe you feel the same like me. It should be the center. The center image is the best, because this one, because the radius is very low, so now the ideal filter will affect the image, because of course the ideal low pass filter, if you choose the cutoff frequency close to the center, then it's become blur. That's why you can increase the cutoff frequency, so it become a little bit sharp. But of course you cannot go further. Let's say if you add more, like this one, if you increase into 100, the cutoff frequency to 100, then you see there's a noise. So why this happen? Because this is happen because at the 100, it might be the radius here is already touch this peak at the corner. Might be the 100 there already cover also the high value at the corner. So that's why you will see that the noise is appear. So that's why 100 is not suitable in this case. That's why you need to have the cutoff frequency equal to 70, which is the best in representing the restoration process by using inverse filtering of the image, whereby your image is affected with both factor, which is additive noise as well as blurring effects. So I think that's only that's the only part that I need to cover in this chapter. And of course, Wiener filter will not cover in your syllabus. Thank you.